All right, so I'm going to show you how to integrate this using a trig substitution. So we've seen now this is our third one. There's really only three types of trig substitutions. When you're given x squared plus 1 or any variation of that, it could be x squared plus 4, x squared plus 9, x squared plus any number. Typically, these are perfect squares. This is where you use the substitution x equals tangent, because you'll create a trig identity that you can then use tangent squared plus 1 is equal to secant squared, okay? Now, if you're given 1 minus x squared, that's where you make the substitution x equals sine u. Because in this case, you're going to get 1 minus sine squared, and then you can use the identity cosine squared. Okay, so the third type is what we have here, x squared minus 1. In this case, it's 4, so that just changes the value in front. But when you have x squared minus 1, you're going to use x equals secant u, because you'll be able to use the secant squared minus 1 equals tangent squared u identity. So these are the three. There's really only these three. If you have any variation of x squared plus 1, 1 minus x squared, or x squared minus 1 inside of these problems, then you are going to use these identities. Now, you can see that 2 and 3 are kind of interchangeable. It's more if there's inside the radical. If they're inside the radical, that presents problems. That's why you have these ones specifically. So in this problem, we're going to use this one. All right, so we say we want x equal to 2 secant u, though, because when I square the 2, I want it to match up with the number in the back, which means dx is equal to 2 secant u tangent u du. Okay, so we can replace everything in the integral. 5 over x squared, which is 2 secant, 4, back up, 4 secant squared u minus 4 times, and then x dx, x is 2 secant u times derivative, which is 2 secant u tangent u du. Okay, so I've done all of tangent u. Gosh. All right, so let's do a couple things. Let's factor let's put these 5 times 2 times 2 together in the top, so 20. I have a secant squared u in the top, and I have a tangent u in the top, du. And the bottom, I'm going to factor the 4 out to get secant squared u minus 1. Okay, which means I can now divide the 20 by 4 and get 5, and I'm going to throw that 5 in front. So 5 goes out front. I end up with a secant squared u tan u up top. I end up with secant squared u minus 1 on the bottom. That's where I'm going to use my identity. That's the same as tangent squared u du. Oops, du's outside. I'm going to come over here. So then I can cancel a tangent. And I have 5 integral secant squared u all over tangent u du. Now what? Well, this is a whole other level of fun. You need to recognize that the derivative of tangent is secant squared, and he's sitting right here up top. How perfect. So it's a u sub. We already have u, so you've seen me do this strategy where I'll just use another variable. I'll say let w equal tangent u. So dw is equal to secant squared u du. And then I will plug all of this in. So 5 integral secant squared u du is just dw. And then it's 1 over w. So I'm doing u sub. I'm just changing the variable because I've already used u once in the problem. All right. Now I can integrate. 5 integral of that's not so bad at all. It's just natural log of w. What was w? It was tangent u. So put that back as 5 natural log tangent u, but I can't have u in the problem either. So now I got to go back to what u was. Well, right here, I set up my relationship for how x and u are related. So I have x equals 2 secant u. Divide by 2. And I have this. Now I'm not going to arc secant. It's kind of weird. Instead, I'm just going to go straight to the triangle. So if I have this angle, which is u, because it's the secant of this angle, secant is the opposite of cosine. So cosine is adjacent over hypotenuse. We have hypotenuse over adjacent side. So secant is hypotenuse over adjacent side. So now we can just find the tangent of that. The tangent of that is, well, we need the adjacent side. So we got to use the Pythagorean theorem. And we're going to get x squared minus 4. And that popped up in the original. That means you're on the right track. If you look at the very beginning problem, we had x squared minus 4 inside the denominator. So that means we're probably on the right track. So from this, we can get the tangent u is adjacent or opposite over adjacent. And we can put that in right there. Final answer, 5 natural log of x squared minus 4 over 2. Now, you may be thinking, this does not look like the answer I got when I did it the other two ways. True. So let me show you how you can make it. When you divide, and we're going to practice this more next week because this comes up in partial fraction decomposition. When you have two things divided by each other inside of a log, you can split it up as the natural log of the top one minus the natural log of the bottom one. But actually, I'm going to do one thing real quick because what do I want to do? Don't want to do it that way. I want to do it this way. Back up. Other thing I can do real quick. Change my mind. Let's do this. We're going to do that in a second. I'm going to write this as natural log of x squared minus 4 all over the square root of 4. Which is 2, right? So I can do that. Which means the, oh, no. I was right the other way. Sorry. Keep it the way it was. Gosh. I want to keep it like this, like I was doing. That's what it was. Okay, I do want to split it up. Gosh, I'm all over the place. Okay, I do want to split it up. There's a couple ways you could do it. So I do want to split it up, and I want it as 5 natural log of that one minus the natural log of the other one. Okay, fine. Then, if you notice this, that's what I was trying to do. I can write this as natural log of x squared minus 4 to the 1/2 minus natural log of 1/2 with a 5 in front because I'm distributing the 5. The reason I did that is because this is where we can use the log property that says if you have a power up here, you can move it outside to in front. If it's the natural log of the base to a power, there's a power rule of logs that lets you move it in front. Sorry, that's what I was trying to do. And this is what you should have ended up with, or some variation of this, when you did yours. Now, you may have had your answer and then minus this. So you may be thinking, well, what the heck is this extra thing? This is almost like a C value. Think about it. When I take the derivative, this back thing is just a numerical value. The derivative of that is just 0. So it really is the same. You just have this extra component in this version when we simplified. Now, your answer may have looked like this. 5/2 natural log x plus 2 plus 5/2 natural log of x minus 2. When you did your partial fraction decomposition. But if you factor out a 5/2, you can do something when you have two natural logs like this. It's the product. It's kind of the opposite of what I did here when I split it up as division. When it's adding, you can multiply the two bases together. So 5/2 natural log of x plus 2 times x minus 2, which gets you the answer that you get when you do u sub. Okay, so sorry, I got a little tricked up on the simplifying logs because I forgot the way I wanted to do it in this class, but That's the whole process, okay? We're not going to focus a ton on trig integrals this year, trig substitution, but these are the 3 major substitutions you do. And then you just have to go through it and see what strategy pops out. So the hard part usually is when you get here, is you have to be clever about how you're going to manipulate this. And we've seen 3 very different types of problems when we got to this point. Sometimes they're obvious, sometimes they're very difficult. This one wasn't too bad, but again, that's it.